All right, we're going to do some problems here where we find the derivatives of some hyperbolic functions. And in order to do that, we need to have a few formulas. And what we have here is that the derivative of hyperbolic cosine x is equal to hyperbolic sine x. The derivative of hyperbolic sine x is equal to hyperbolic cosine x. And actually, I think that does it for here. Well, let me just say that if you know the derivatives of the trig functions, then it should be easy to find the derivatives of the hyperbolic functions. All right, now, see, as we see, hyperbolic cosine x, the derivative is hyperbolic sine x. Now, some of the derivatives for the hyperbolic functions have a negative in front. And those functions that have a negative are the ones, for example, like hyperbolic cosecant x. It's those functions that are reciprocals functions, like hyperbolic cosecant x, hyperbolic secant x, and hyperbolic cotangent x. The ones that are not reciprocal functions, and that's what which I am calling not reciprocal functions, would be hyperbolic cosine x, hyperbolic sine x, hyperbolic tangent x. Those things that are not reciprocal functions don't have a negative in front. So now I guess I'm in for a penny, in for a pound, and I guess I'm going to start writing more of these. But we don't need all of these for this video. But hyperbolic cosecant x is negative. Okay, so it's negative hyperbolic cosecant x, hyperbolic cotangent x. And so these look very similar to the derivative formulas of trig functions, but for the derivative formulas for trig functions, it's the ones that have a that have a negative in front. But for, derivative cosine x, derivative cotangent x, derivative cosecant x, those all have a negative in front, while here for the hyperbolic functions, it's the ones that are reciprocals. So in fact, I don't even really care about that one there anyway. So I just was pointing that out, how you can memorize this. For here, we're going to use the chain rule, and we have a composition of the hyperbolic cosine function with the function 3x plus 1. So we look at the outside hyperbolic cosine, take that derivative, which is hyperbolic sine, and then we keep the inside function exactly the same. So that's how the chain rule works. But then we multiply by the derivative of what's inside. And the derivative of what's inside is 3. All right, so that's the chain rule. So that's the first one. So we take the derivative of the outside, which is hyperbolic cosine. And when I write down that derivative, I write hyperbolic sine, and I leave a blank space. And in that blank space, I put 3x plus 1. All right, then I multiply by the derivative of the inside, and the derivative of what's inside is 3. All right, so that's what gives me the answer there. Okay, so that's the first one. The second one, also chain rule. I take the derivative of hyperbolic sine, which is hyperbolic cosine, and then I leave the inside exactly the same, but then I multiply the derivative of x squared, which is 2x. So again, that's the chain rule. So you take the derivative of the outside function, which is hyperbolic sine, that's outside function hyperbolic sine, and that derivative is hyperbolic cosine. And then I multiply by the derivative of x squared, which is 2x. The next one's a little bit more tricky. You could do it two ways. You could use the quotient rule, or do what I'm going to do, which is the chain rule. And I write this as hyperbolic cosine x to the minus 1 power. And when I do that, I do not mean an inverse function. I mean literally, as we see over to the left, the reciprocal of hyperbolic cosine. And when I take the derivative, I use the chain rule, which is the power rule of, say, u to the minus 1 power. So I have negative 1 u to the minus 2 power, and u is the inside, hyperbolic cosine x. And then I multiply by the derivative of what's inside, which is hyperbolic sine x. So y prime is equal to negative hyperbolic sine x divided by hyperbolic cosine x squared. And the thing is, I'm trying to imagine, I didn't look at the answer in the back of the book, but it wouldn't surprise me, I have a feeling that they would write this, that someone possibly would write it like the way I'm showing here. Hyperbolic sine over hyperbolic cosine. 1 over hyperbolic cosine, which would be hyperbolic tangent x, hyperbolic secant x. I don't know that that's what they're doing, but I sort of think that's the answer that you might see in a book. But in the back of the book, but it might just look like that. Either one's fine with me. This one's also chain rule. The derivative of sinh, hyperbolic sine, is hyperbolic cosine. Then I copy and paste the inside. Then I multiply by the derivative of what's inside, ln x, that's 1 over x. So that does that. The last problem is okay, so we have those there. The last problem is a word problem where you have a chain that is a chain that hangs from 2 posts. And the chain is, the posts are 2 meters apart. And this is described by this function, y equals 2 hyperbolic cosine x over 2 minus 1. And apparently this is, this is an observed fact, and then this function models that. So we take that as a fact that a chain hanging from 2 points will form a catenary, and the catenary has this equation. So that's sort of interesting. I haven't seen what that derivation is, how they know that's true, but I believe from different books that that's true. Okay. What they're asking us to do is find the slope of the catenary at the left endpoint, at the left fence post. So essentially, we find the derivative at -1 because the slope of the tangent line is the derivative. That's what we're trying to find. So we're trying to find the slope of the tangent line, and that's the derivative. All right, so f of x is 2 hyperbolic cosine x over 2 minus 1. We use the chain rule. First, we leave the 2 alone, but the derivative of cosine, hyperbolic cosine is hyperbolic sine. Notice there's no negative. For hyperbolic cosine x, the derivative is hyperbolic sine x. Okay. Then we have what's inside, which is x over 2. Then we multiply by the derivative of x over 2. So the derivative of what's inside is the derivative of x over 2. Well, that's the same thing as taking the derivative of 1/2 x. So that will be 1/2. Minus 1. Well, the derivative of minus 1 is 0. So we get f prime of x is 2. Well, hold on. So, pretty clearly there is cancellation here, and between those 2 and this 1/2. So we get hyperbolic sine x over 2. And so the derivative at -1 is hyperbolic sine -1/2. And I think somewhere I have, sort of ruined the video if I do this at the very end, but somewhere I have the solution. These are all taken from Openstax, and here's the solution. Sort of takes the fun out of it if it's, you see I'm just copying this down, but the solution apparently, well, this is the solution. What I'm saying is that some people feel more, at ease if they have a decimal approximation. That's certainly an irrational number. These are taken from Openstax Calculus. That's which you find at openstax.org. So you go to openstax.org and you look at Calculus Volume 1, and you get the problem. All right. I don't really feel like taking out calculators and so forth. But by the way, remark if you can't find that button in your calculator, which wouldn't surprise me, I mean, for me, hyperbolic sine x is e to the x minus e to the negative x over 2. That's by definition. Hyperbolic cosine x is e to the x plus e to the negative x over 2. And so if you are using a calculator, you can use the exponential button. And if we look over here at this picture, which I tried to, which I drew with the aid of a graphing program. Well, this picture so far is from the aid of a graphing program. The tangent line then apparently has slope 1/2, and now this picture is fairly accurate because it comes from a graphing program. But whether my tangent line picture is that good, I'm not so sure about. But I'll try to draw a line with slope negative 1/2 because this is negative 0.52, so it's around negative 0.5, negative 1/2, and so that's sort of what we're looking at. We're looking at the tangent line, and we're looking at the slope is f prime of negative 1, which is around negative 0.521. So that's the answer. I mean, I think the most interesting thing about this is simply the fact that a chain hanging between two posts might look sort of like a semicircle or maybe like a parabola, but it turns out that what it is what's called a catenary, and a catenary is given by an equation as shown in this case, y equals 2 hyperbolic cosine x over 2 minus 1. So, all right, that finishes that. Goodbye.